Hi, I'm Roy and I'll be presenting our work titled MobileVOS, Real-Time Video Object Segmentation, Contrastive Learning Meets Knowledge Distillation. This work was done with my amazing collaborators Mehmet, Bruno and Albert at Samsung Research UK. Video Object Segmentation, VOS, is an important problem in computer vision and it has a lot of interesting applications in video editing, surveillance, autonomous driving and augmented reality. Unfortunately, most recent advances in this domain are ill-suited for mobile applications where there are limited computational and memory resources available. In this work, we propose a novel application of knowledge distillation for VOS, followed by a unified framework with supervised contrastive learning. We then introduce a few modifications to the existing space-time memory networks and adopt a finite memory window to meet mobile resource constraints. The combination of these components leads to competitive performance with state-of-the-art despite being up to 5 times faster and with 32 times fewer parameters. Video object segmentation is when you try to find and follow objects across multiple frames in a video. However, in our particular work we focus on what is called semi-supervised VOS, or SVOS, which is where you only get a description of the object in the first frame. SVOS is especially difficult because you have to deal with occlusion and drift, all while performing well in a class-agnostic manner. When it comes to SVOS, there are 3 main ways to do it: online fine-tuning, object flow, and offline matching. Recent works have been using memory-based methods, which is where you store previous frames in a memory bank and then use them to predict the next object masks. These methods are really good at finding feature correspondences, but they have one main problem: they incur a significant memory overhead. Some works have tried to solve this problem by only storing a few frames, only working on keyframes, or even proposing a complex overhaul of the memory model itself. But even though these methods show strong performance on high-end computers, they are still too large and expensive to work in real time on mobile devices. In our work, we introduce a new approach called MobileVOS, which are a set of high-performing and efficient models that work on mobile phones thanks to a novel distillation loss during training. To construct these models that can attain real-time performance on mobile phones, we propose a few simple modifications to the existing space-time memory networks. Firstly, we propose to use a much smaller backbone for the query encoder. Secondly, we reduce the memory bank to only store the most recent and first frame features, thus bounding the overall memory consumption, which can be very significant for longer videos. To encourage these features to be temporally consistent, we then perform distillation from the much larger pre-trained and infinite memory counterpart. We propose to use a pixel-wise representation distillation loss to transfer the structural information between 2 models. A pre-trained infinite memory model is used as the teacher, and a small finite memory model will then be used as the student. Both of these models are fed the same augmented frames and a distillation loss is applied between them. This loss involves constructing correlation matrices from the 2 sets of representations, where each matrix captures the relationship between all pairs of pixels. The representations, denoted as ZS and ZT, are chosen to be directly before the final pointwise convolution and upsampling layers. The final representation loss is then derived and motivated from information theory. In simple terms, this loss formulation is equivalent to maximizing a surrogate estimate for mutual information between the student and the teacher. The majority of prediction errors occur on the edges of objects, and constructing a correlation matrix for all pixels is computationally intensive. In response to these challenges, we propose a sampling strategy that only selects pixels around and near the edges of objects. This strategy restricts the distillation gradients to pixels that lead to prediction errors, while making the formulation much more computationally efficient. Furthermore, we observe that this modification has the added benefit of improving the overall model convergence. The effectiveness of knowledge distillation alone can be dependent on the relative capacity gap between the student and teacher models. More formally, this training regime scales poorly as the capacity gap diminishes. To address this constraint, we propose a generalization of our loss to encompass pixel-wise contrastive learning. Since we already have the dense ground truth labels, we can construct an additional target correlation matrix as shown on the current slide. We can then couple the two target correlation matrices to provide a way of interpolating between these two training regimes. By considering the case where omega equals 0, the loss will now reduce to a familiar supervised contrastive learning setting. We proposed an extensive evaluation of our proposed MobileVOS models and distillation pipeline on both Davis and YouTube datasets. We also include a comprehensive re-evaluation of recent works in the literature regarding their latency and memory requirements, to demonstrate the improved performance in practice. To confirm the theoretical motivation, we qualitatively demonstrate that our distillation loss is encouraging more temporally robust features, and finally show the generalizability of these models to out-of-domain videos, image painting, and on-device segmentation. We compare MobileVOS against previous state-of-the-art methods on the Davis 2017 validation split. The results are shown in the following table, in which our best performing model outperforms SDCN by 0.3 JNF, while being just 0.2 shy of RDE-VOS, despite running 4 times and 3 times faster than these models respectively. Additional experiments on the Davis 2016 and YouTube VOS can be found in our original paper. To conduct a fair comparison of the computational cost of previous works, we provide an extensive evaluation of MobileVOS and other methods on the same set of hardware. We consider both the server-grade NVIDIA A40 and a desktop-grade NVIDIA 1080 Ti. In all cases, we use the author's provided code, but with a modification to accept randomly generated video sequences of 2 different durations. The results can be seen in the following table, and show that our MobileVOS models are significantly smaller while retaining a constant low latency across both the short and long duration videos. Our smallest model has an inference latency of 32 milliseconds per frame on a Samsung Galaxy S22, thus opening the doors for real-time SVOS solutions on device. Thank you for listening.